high as compared to the lower one, which is very small in case of the monomer, which is very aggressively move on the surfaces. Diffusion prefactor, which is actually providing the attempting frequencies, and these are the parameters, and which provide the all story of the diffusions of the surfaces for the islands. Copper trimer behavior at the silver one surface. We have saw over that in the presence of the copper, there are some fissures and dislocations. Trend through dislocations are appearing on the surfaces due to the weight of the island. And on the other story, we can say that here the copper silver bondings are overcome on the silver bondings, and that's why the silver atoms a little bit stretch towards the island, and we saw that there are some fissures very near to the, which are near to 2 angstrom to the island, and 2.5 angstrom dislocations are appearing. And the lower one picture actually representing some vacancy formation. There red colored are actually island atoms, while the blue colored atoms are the substrate atoms, which is silver over here. Here we saw that with the increase of the temperature at 700 Kelvin, the substrate atom popped up, means the surface atom becomes absorbed atom, becomes a part of the island. This is indigo color actually representing here, which was the part of the surface, and now it is popped up, and now it can move on the surface, and it is not the part of the crystal right now. But during the diffusion, we saw with some passage of time, one atom of the copper absorbed in the surface, which is representing by the last picture, which is with the green color here. This atom take the position of the surface and becomes the part of the surface, and now the adsorbed cluster here, 3 atoms are not the same type of atoms, 2 copper and 1 is the silver, which can move on the surface. They can move, but we saw over here that the copper atom size was less than the silver. That's why there remains some lapse well over there. Already this is the well which is created by the vacancy formation, by being a atom pop up knocked from the surface. Then other one atom which was the part of the island now becomes the part of the surface, which is representing by the green color here. Remaining some lapse well over here, because the size of the copper is less than the size of the silver. Due to the lapse well, this island remains stick to that well, because there is some kink for the island. It's difficult for the island to move from that position. So at very high temperature, it moves from that one. No doubt it moves. However, it stick for a time, almost 40 to 50 picosecond on that position, where it makes some exchange of the substrate atoms with the island atom. We also saw that the migration of the vacancy here, left one actually representing the rectangles, actually representing the dislocations, while the circles are representing the fissures. We can saw here the migration of the vacancy, the yellow colored atom, which is right side of the in left picture, and the right one we can see this is on the top and the left side. Right picture, that yellow colored changes the position. This yellow colored atom actually makes some sense of migration of the vacancy, and the popped atom is now indigo color is lower one. We saw that with the passage of the time, this is actually in 0.5 picosecond. We saw that the dislocations, the dislocations are attracting each other. They come closer to each other, while on the other side the fissures, they moved away. And on the other side, we can say that the defects are attracting each other. These dislocations are the normal defects of the crystals, while the fissures are the gaps which developed due to the atomic oscillations. They cannot attract each other. No way. They have to move away each other, while the dislocations are attracting each other. In next slide, this is the snapshot of the ternary copper zirconium silver alloy. This is actually very interesting results. These are three atoms of the species. Those combining the cluster, trimer, hexamer, and the nonamer. These are the pictures of the. I actually hexamer is missing right now. Trimer and nonamer and the decamer. These are the different snapshots, and we saw that there is a formation of the vacancy in second row, and some migration of the vacancy in third picture, and then some migrations, that is atomic diffusions due to the island. On the other side, we saw without these islands, there is no this type of the defect. These defects are that actually due to the weight of the island and the forces between the host and the guest atoms. And these actually host guest atoms, the bondings overlapped on overcome on the bulk bondings, and that pull the atoms from the surfaces. And we saw that these make some inharmonicity. These create some disturbances on the surfaces. These change some fields on the surfaces. And we also saw some exchange of atoms. Blue colored atoms are actually right now in part of the island. This is the atomic exchange process here, which was seen in the previous one, how surface silver atom becomes part of the island, while on the other side, the island atom becomes part of the surface. Here, actually, zirconium atom is too energetic in this one, which is a lighter one, and it's so mobile, and it is it becomes part of the surface, and atomic exchange process is just represented here. These are blue colored atoms are actually the surface atoms, while the I atom, which is the surface atom, it how it gets the position of the surface, and the surface atom K, which is going to pop up. This is the whole story of the atomic exchange process. Center of mass for the ternary copper zirconium alloy cluster, and we saw that this is the whole story of the variation of the center of mass for the trimer, hexamer, nonamer, and the decamer. We saw that the trimer is moving very frequently, and a little bit this is was seen in the hexamer case, while in the case of nonamer and decamer, the dark spots are representing that it stays for enough time island over there. And for the decamer, the very small diffusions are found over there, but with the increase of temperature, we saw some diffusions because the island size is right now increased, and there is enough energy required to move the atoms, to change the position of the atoms. This is the potential energy of the ternary copper zirconium silver alloy cluster. We saw the variation in the potential energy of the island with the passage of the time. There are certain jumps; those show some anharmonic features. We saw that over some breakage of the island. This is actually your sudden jumps actually representing the breakage of the island, some distortion and anharmonicity in the crystal. These are the conclusions. We can say that this is actually how the simulations are going, and we can show some the movie of the whole story. There is two large computational resources behind the story, and I just basics are given over there, while the big calculations and the big potential bondings and some interactions and so many algorithms are involved behind the story. And this is the island atoms which are the diffusing on the surface, while these are the atomic oscillations. Keep in mind, these are the oscillations which are in angstrom. These are in angstrom, cannot be seen with the naked eye. If we take some dot on with a pen, then the millions of atoms can be over there. While here we are taking only 2400. These are 20 by 20, 400 atoms, blue colored atoms, while the 3-4 atoms are on the side. And these dynamics are at 700 Kelvin, which is a little bit. We have to focus 700 Kelvin. There's enough temperature, which is roughly cannot be achieved by simply way. We have to make some special configuration to do all these experimentally. We saw that with the increase of temperature, there are a number of things are going to increase. With the size of the island, diffusion is going to decrease. And the harmonicity defects, blah blah blah. All these things were very long things, and these are actually helped us to avoid those problems which can be make some sense during the some physical calculations. If there are some atoms absorbed on the surface, they may change their physical properties. You people have some idea during the workshops. Always they are going to make the clean things, because those atoms which may be absorbed on the surface may can uh, change the as a whole story. That's why these are the actually calculations which can give some idea about the experimentalists, how they can mm, adjust the things, how they can control the things, how the parameters can affect the things.
सजा साहब आपकी स्लाइड्स क्यों नहीं हो रही?
I finished the slides.
Okay, that's fine.
You have seen the movie? At the end, I saw some movie. I showed some movie. You saw the movie?
No, sir.
You were disconnected. I didn't disconnect. I think.
Yes,
You can.
somehow, because I'll change the laptop now, so there is some problem with my laptop. Then I have changed.
Movie. You cannot see my screen right now.
No, sir.
Still not, sir.
Okay. Okay, it's working right now.
जी सर. हेलो सर, मेरी आवाज आ रही है आपको?
Is writing all things.
Okay, sir. Thank you very much, sir, for your great presentation, Dr. Saab. So, is there any question from the audience? Hello. Sir, I am working. कोई question आया है? I will read here. I am working on DFT calculation at University of Geoscience, Wuhan, China. Nice to hear, Dr. Sikandar Saab. Good initiative by Dawood University to hear and meet the researchers. Thank you. Just only for the compliments. Thank you very much for your great presentation, and we also look forward in future very great initiatives, and again we will improve our networking, and we will ensure that inshallah all the researcher on one page one day. Thank you very much, sir. Now I would like to introduce one of the great scientists of our country, Sir Abdul Malik Saab from the National Institute of Laser and Optronics College. Abdul Malik Saab, over to you, sir. And I welcome you, and good evening from Karachi.
Thank you very much. First of all,
हाँ? ये तो ज्यादा मेरे ख्याल मैं इसको लीव कर सकता हूँ. मेरी हो गई है बस.
इसका क्या होगा? वो मिलेगा सर्टिफिकेट वगैरह मिलेगा आपको?
क्या?
सर्टिफिकेट वगैरह मिलेगा?
कुछ हाँ, वो भी आएगी इस तरह की चीज भी. ना तुम लोगों ने जब मैं करने वाला था तुम उठ के चले गए.
मुझे तो समझ नहीं आती इसकी ना.
तुम्हें तो नहीं काम है यार.
Abdul Malik Saab, sorry. Sikandar Saab, thank you very much.
मैंने कहा कि जाओ. कोई हाल नहीं यार तुम्हें. ये तुम्हें.
Hello.
Over to you, Abdul Malik Saab.
Yeah, I want to share my slides first. Hello. Hello.
जी सर,
Shankar,
जी सर, जी सर.
my presentation is looking to you.
Yes. ये फर्स्ट स्लाइड पे आ जाए सर. Okay, thank you.
Slide running.
I welcome you, sir, here in this symposium.
Thank you very much. Hi, dear distinguished scholars, engineers, faculty members, scientists, industrial experts, and all other worthy participants of NM's Talk 2020. Assalamu alaikum. I hope you and your families and loved ones are well and healthy. And first of all, I would like to thank Dr. Engineer Sajid Hussain Syal Saab, Chairman and Faculty of the Metallurgy Engineering Department of DUET University Karachi, for extending all the excellent arrangement in the successful holding the symposium and giving me an opportunity to present here. With this best wishes, I will start my presentation. The topic, Advanced System, Designing and Simulation, Characterization, and their Fabrication. I will present here. Sir. Sorry. Okay, wait, please. Presentation. Okay. Rotate. There is no full screen option here. Is it okay? No full screen option here. Again. I have shared. Is it okay? It's open. So I will start my presentation. The topic of my presentation is designing, simulation, characterization, and fabrication of an advanced nanosystem. My presentation outlines, I will introduce the nanosystems, nanosystem material, its designing, how it simulate, nanosystem materials, how it synthesize and grow, and nanosystem, how they will be characterized and analysis. And then I will go to the fabrication and development. Nanosystem, a definition, working with the matter down to the molecular level to create the structure and device 1 to 100 nanometer in size with fundamentally new organization, properties, and performance. We can say a nanosystem is an instrument that responds to a physical stimulus such as heat, light, sound, pressure, magnetism, or motion. That will take us to the realm where the properties of the material are dramatically different, demand new tools and new understanding, may hold the key to 21st century industrial revolution. Advanced nanosystem, I can say, if all the nanostructures elements operate at the same frequency, high degree of mutual coherence, and emit, sense, detect, or generate in phase with respect to each other, then we can say they are integrated, all the nanosystem. For example, nanolasers, nanogenerators, nanosensors, and nanodetectors are examples of nanostructures. The array are extremely tolerant to a latest constant variation, allows composition to vary over a large range within a single substrate or structure. How nanoscale material categorization? Naturally, ultrafine particles are virus 10 to 60 nanometer, bacteria 30 to 10 micrometer, dust from desert 100 nanometer, and the ultrafine particles from established technology or by product the conventional process, combustion soot 10 to 80 nanometer, paint pigments 80 to 100 nanometer, welding fumes 10 to 50 nanometer, and diesel exhaust particles, small modes 7 to 40 nanometers. Carbon black of photocopier toner 10 to 400 nanometer. Engineered nanoscale particles that are nanomaterials, chlorine, buckyballs 1 nanometer, nanotubes 1 to 5 nanometer, multiply of 10 micrometer, and quantum dot for medical diagnostic 5 to 20 nanometer. Semiconductor bars of sensors 10 to 100 nanometer diameter, multiplied 1 to 1 micrometer. Why nanosystems are attractive? That is useful for information technology and quantum informatics, quantum electronics, just like logic memories, magnetic memories, spintronics devices, and for energy, large-scale, low-cost nanoparticle based on solar energy collection, high-efficiency solid-state lighting, and for health in situ drug delivery, diagnostic, action monitoring, performance enhancements. Environment, low-cost nanosensor array for health safety, nanoparticle-based waste destruction, and manufacturing large area bottom-up assembly for low-waste, energy-efficient manufacturing. How to build things at nanoscale? Conventional machines, 1 meter to 100 millimeter, just be built and assembled. And for microelectronics, 10 to 0.1 micrometer top down, just built in place. And for nanotechnology, 1 to 100 nanometer bottom up, self assembled. How to build things at nanoscale, making nanomaterials. First of all, self-assembled, top-down, bottom-up, characterization of these nanostructures, imaging and measure the small things, understanding the properties. Nanoland lies between micro world and single atom and molecules. Nanosystem integration and performance. This is the high payoff area. How do we assemble the nanostructure into advanced nanosystem? Properties and application of nanosystems. Properties: mechanically strong and flexible, optically transparent, tunable optical band gap, monolayer drag proof, sky jackets, wrinkle resistant, stain repellent, deep penetrating skin cream, world's first OLED digital camera, nanotex DVD and book collection, performance sunglasses, nanocrystalline sunscreen, and the 9 antenna high-tech tennis rackets and balls. Now I come with this motivation introduction to how they designed and simulate the nanosystems. First of all, the material for these nanosystems. As you know, the designing and simulation for a nanoscale, we need a high speed of fast computing systems. So The construction of mathematical model, analysis of idealized models and hypotheses to describe the nature, physical phenomena by performing the idealized experiments on the clusters of computers. The triangular show, first of all, we have to do a computational design, then predict by experiments and theory development, predicts, and again, it's a cycle test, predicts, test, and it's go on. The cluster system for these nano system for designing computers having Linux or Unix or ROX operating system. We have used laser mod here, Win2K, the density function theory codes, quantum espresso, ANSYS for micro scale or MEMS devices, and also a console multiplex code for MEMS type devices, realistic atomic program code and Monte Carlo, and some of Mathematica and MATLAB and MathCAD codes here. How the cluster, the clusters are working. They are working with a gigabit Ethernet networking modes. First computer master node and other are computing nodes. For example, numerical simulation for droplet surface temperature using console multiplex. We have developed the such theory. The boundary conditions consider the temperature fixed from droplet, substrate base temperature is fixed, and heat flow droplets. Numerical simulation of the droplet temperature using console. We have calculated such properties, construction, concentration, diffusive flux magnitudes, and the time scale with respect to the its spread. Comparison with these with the published data here, the console simulation, time versus temperature variation, surface temperature for substrate copper at 60 degrees centigrade, you can see here, and cross-section glass substrate for copper at room temperature. And the important factor now I want to share, energy band gap. Energy band gap of a nanostructured material is one of the most important parameters for optoelectronics application. It determines the spectral features of absorption and emission process and other electronic and optical properties. Range of the band gap relies with high quality nanostructured material like chemical and thermodynamic limits. Traditional planar epitaxial method is severely limited due to the requirement of latest matching. Larger the mismatch, nanoscale offered the unique opportunity for growing the nanostructured materials, alloy structures of very dissimilar latest constants and band gaps. And we use density function theory for that. And here is the model for how we can the mathematical applications used for that. And with this theory, using LDO approximation, core electron replaced by the tolerant Morton pseudo potential, and the calculation were carried out with such that is just for example, strontium titanate, bulk latest constant we simulate. And these are simulated by Cobo and Nose, and the results show that as we increase the temperature, theta tends to decrease monotonically as the surface goes through a sequence of the reconstructions. With the help of Win2K density function theory, using a density function theory code, we can find the absorbance. Maximum absorbance take place here from graph show of 1.6 electron volt to 2.6 electron volt. And we can find the energy loss for these such type of nanosystems. Loss of energy during the propagation of light in the material. Initially, there is no loss. As the incident photon energy increase, there become maximum loss at 14 electron volt. Above the value of material behave as a metallic and below this electric. The other optical property, how many electrons are taking part in the optical transitions are calculated with the help of some rule by Win2K. With the increase of energy, number of electrons are increasing. Maximum peak is obtained at 18 electron volt. It means 18 electrons are taking part in the optical transitions. And the other such function, dielectric functions, the real part and the imaginary part we can find. And with this, we can simulate the optical properties of that material. such like the refractions. At some value, reflective index value is maximum. At some value falls below unity. The reason is the material absorbed at high energy photon at higher values. Maximum refractive index is obtained at first transition, and a higher value lower the refractive index show that the direct de-excitation is not possible. Energy dissipate. And the reflectivity, maximum reflectivity obtained at 2.5 electron volt with some humps. These humps show that the inner band transition of the electron, and at maximum value of the reflectivity, semiconductor property material vanish and it behaves as a conductor at a high incident photons. And at the end, with the help of density function theory of Wien-2K code, band structure calculation is a skill to investigate the material, whether conductor is insulator or semiconductor. With the help of this, valence band minima and connection band maxima lies at some symmetry points. They satisfy the direct band gap. And in optoelectronic devices, direct optical transition dominate over the indirect transition variation, 0 to 0.2 in our cases. The system was the CZT. And the density of states, we can also calculate total density of the state, gives the information about the collective behavior of all the materials. No peaks above 0, red and black lines showing the band gaps, higher peaks showing more number of density of state at a particular energy range. How the nanosystems are synthesized or brought. We are using here in our institutes also, there is a molecular beam epitaxy. When we did the calculation, density function theory calculation, then go to the such type of system, nanosystem. MB is an ultra high vacuum evaporation technique for deposition of extremely high purity crystalline thin film with the atomic precision. You can see the low log chamber etc. here, and it is used for growing the epitaxial layers on a single crystal wafer and for in situ surface analysis. We have hafnium cells, gallium, indium, aluminium, silicon, magnesium, and beryllium etc. more. And this is equipped with the nitrogen RF plasma source, and also it is equipped with the in situ characterization tools, reflection, high electron refraction, read, and spectroscopic ellipsometry. With the help of that, we can real time characterize the growing nanostructures. For example, growth and crystallization gallium nitride and gallium arsenide based light emitting nanosystems. It's a LED or laser diode. First of all, we designed it with the help of laser mod, and the laser mod, we can calculate the thickness of the layers and materials used for, and the optimized structure for LED or laser diode. For example, epitaxial growth of gallium nitride or aluminum oxide plasma assist MB and its characterization by REAT, N-type doping silicon of gallium nitride for gallium nitride, and P-type doping magnesium for gallium nitride. Growth and characterization of indium gallium quantum well structure, and growth of the semi-insulating gallium nitride for radiation detectors, etc. And from figures, you can see the optimized structure from laser mod, and then the read peaks in situ read images are showing that the crystalline structures are growing, and from the graphs you can see the growth of the single crystal growth of gallium nitride. Another very important system for the nanosystem growth, low pressure chemical vapor deposition here at NILO, LPCVD. That is the chemical vapor deposition technology that uses the heat to initiate a reaction of a precursor gases on the solid substrate. This reaction at the surface is what forms the solid phase material. Its application, just like silicon dioxide thin film deposition and polysilicon thin film for silicon dioxide, and deposition of film for silicon-based microelectronics, production of the microelectronics mechanical system, NAM system, and optoelectronic material, and by CVD, LED, blue laser diode, solid state white lightning. Here you can see the schematic of these LPCVD system in the diagram, and above is the picture of that LPCVD system. And basic technique for thermal electron and beam evaporation, for with the help of thermal evaporation, we can also deposit the nanostructures for nanosystem. The deposition of different nanostructural material like metals, dielectric, semiconductors, nanostructure deposition of the semiconductor materials, thin film for various optoelectronics application, and we can use such type of system for metal contacts, and the techniques are here equipped with a thermal and electron beam evaporation. We can use reactive magnetic spectrum is the second one system. Pulse laser deposition system is also, we have the next picture is showing the pulse laser deposition system. That are used for anti-reflection coating, anti-reflection type of nanostructure material, high reflection coating, beam separators, growth of metal oxide by sputtering and thermal evaporator to study their response to the different gases and different types of material, such like aluminum nitride, silicon carbide, cuprous oxide, zinc oxide, and tin oxide. We can grow with the help of sputtering system, and good quality films we can get. Growth and optimization, high quality crystalline aluminum nitride thin film by using sputtering technique for the application of optoelectronics. Fabrication of cupric oxide thin film based on transistors for application in electronics. And the deposition system. Electrospinning is the fiber production method which used for electric force to draw the charged thread of polymer solution up to the fiber of 10 nanometers. The system is equipped with a syringe pump, nano mover, power position systems, and power supply 50 kV, 0 to 30 milliampere currents, and Dell Electronics Corporation, that is, and the collector is circular copper plate, rotating aluminum drum mesh, interdigitating electrodes. We can spray coating. You know, it is a basic technique. Is the coating technique where a device spray a coating, paint, ink, varnish through the air into the surface. Air brushes spray gun we use here. And next other system is chemical vapor deposition system. With the help of this, the showing nanostructures here in the diagram, optical image of CVD grown indium selenide at the different growth time of the flow rates with different flow rates. Here the flow rates, growth time of the growth speed of both edges would be identical, vanadium, selenium, and indium, which result in the hexagonal shape. At lower organ flow rate, the growth time, the growth rate of selenium edge, vanadium and selenium, and in the edge vanadium, indium is either vanadium or silicon, and vanadium or selenium is greater than vanadium indium. Shape of the flag transferred from circular to hexagonal with increasing the flow rate and growth time. Flag shape depends upon the edge minimum energy of the element in the symmetric crystal of construction model C. Above the schematic of the CVD system, it is just a quad with the which is equipped with a quartz tube and with the optimized flow rates of different gases. How the nanosystems are analyzed or characterized? The system use X-ray diffraction technique. Here at the low, an instrument capability it is used to identify, determine the crystal structures, latest parameters, size of the crystallite, or grain size, texture, stress and strain, mole fraction, composition of light, phase and thickness of the layer of the film. We can use the X-ray technique. Some of CZT X-ray diffraction, peaks as deposited. The above graph show multi-peak after annealing and intensity increases. Little bit shift towards the left show the small concentration of zinc, and CZT11 peak is between CDTE and zinc toroid, 25.77. CZT X-ray diffraction, again 4 peaks in the deposit samples and multi-peaks after annealing. Little bit right shift indicate that excess form of zinc, and sharpness of peak testify their homogeneity. And the next tool after the X-ray diffraction, we can use the field emission scanning electron microscope for morphology. Field emission scanning electron microscope is one of the most powerful and useful tools available today for nanostructures and nano system. SCM use electron rather light to examine the surfaces, permitting much greater magnification, resolving the power and depth of the field. Field emission scanning electron microscope capability provide us the high resolution imaging at magnification up to 10 raised to the power 6 multiplier. This allows us to examine the characterize the nanomaterial fractures, surfaces morphologies, composites, and their constituents and microstructures of the prepared cross section. Through the addition of energy dispersive EDX X-ray spectrometer, we can detect all of the elements above the beryllium atomic number 4 on the periodic table, allowing us to characterize the most material. And the schematic diagram of the field emission scanning electron microscope here. It is designed to perform an imaging with the low energy electron and ultra high resolution at the same time. The model is showing here an instrument capability 1 nanometer up to resolution and magnification 1 millionth, secondary electron imaging, topographic contrast, back scanning electron imaging, phase contrast, energy dispersive X-ray spectroscopy, and the compositional analysis we can done with the help of XRD EDX. Some pictures and some morphologies obtained by field emission scanning microscopy. For example, ZN nanowires, and clearly showing the structure, and these are the polymer fibers, TiO2 nanotubes, Ag nanoparticle on silicon deposited, structures grow, and the image of Ag particle on the antimicrobial dressing, and 10 nanospheres here, and TiO2 microspheres. And for example, EDX of the ZN thin film, we can see the clear zinc and oxides are contents there with the help of EDX spectrum. The next important technique for analysis and characterization of the nanostructure, that are Raman spectroscopy, photoluminescence excitation, and electroluminescence system for electronic optics characterizations. These systems are capable of excitation sources there, helium and cadmium lasers, 325 nanometer and 442 nanometer, DPSL 532 nanometer. And detectors are CCD, indium gallium arsenide. Resolution is 5 centimeter to 1 for Raman and 0.019 nanometer for PL. Temperature range 10 Kelvin at to room temperature. We can find the spectra with the help of such type of Raman systems. With the help of Raman system material, we can identify the materials, structures, crystallinity, phase transition, polymorphism, and with the help of photoluminescence system energy, we can find out the energy band gaps, identification of impurity levels and defects, and material quality also we can find with the help of photoluminescence. Let's suppose CZT Raman spectroscopy here. The sharpness and broad peak indicate how well and in much quantity that material exists. Redshift after annealing indicate that the increase of zinc concentration. Above figure, compare the above graph with the bottom below graph, we can see clearly the difference of the Raman spectroscopy. With the help of this Raman spectroscopy characterization, that show the increase of zinc concentration. With the help of photoluminescence, single substrate by controlling the spatial variation of the various elements and the temperature of a substrate called the dual gradient method, we observed wide spectrum of visible light from different parts of substrate by optical pumping. The image clearly shows the different colors with the help of just the concentration of CGTE and zinc telluride ZNTE. We can change the color of CGT growth nanostructures. And over a wide range, we can use this type of material for emission detection and also for other purposes. The other important technique for electrical properties measurement, we can find the IV and CV and Hall measurement systems. This system equipped with the that is 4 SMU and 4 amplifiers. Input impedance 10 per 16 ohm, accurate, greater than 10 per 16 ohm, accurate low current, pico ampere, no leakage current due to the mechanical switching software used IV, CV, and Hall measurements. Resistivity we can find from such type of system for method. Resistivity we can find conductivity, mobility, doping concentration with the help of such type of Hall measurement system. And another important technique which can be used for morphology for nanostructures. Morphology of nanostructure can be in 3 scanning modes of atomic force microscope. One is the contact mode, non-contact mode, and tapping modes. The application in organic materials and organic materials surface morphology, we can find out the roughness, surface potential, and film thickness. For example, here is the tin oxide prepared by electron beam film, the topography of the such nanostructure, and here is the silicon grating of the by another is the spectroscopic ellipsometer. Instrument capabilities: light source, xenon lamp, detector photodiode array, spectral range to 80 to 100 nanometers, 1000 nanometers. We can find with the help of this thickness of the thin films, multi-layers thickness, dielectric constant, refractive indexes, and extension coefficients with the help of spectroscopic ellipsometers. And then here also